Greetings, ladies and gentlemen. We're going to continue our discussion of mechanisms today, and today is Triangle Day. Every mechanism we do today will have a triangle intermediate. You guys know a little bit about triangles? What do you know so far? In terms of chemistry, organic. They're not very stable. Why not? They have strain. What two types of strain do triangles have? Angular strain, because the angles inside of a triangle with equal sides is 60 degrees. That's very bad compared to 109.5 for an ideal sp3 hybridization, right? And they have torsional strain, because when you're flat in a ring, you'll have adjacent atoms that have H's in front of H's or groups in front of groups. We call that eclipsing, right? And it's called torsional strain because the normal way to get away from eclipsing is to rotate the carbons, right? Look, they're eclipsed and now they're not. But when your ring is size 3 or 4, they're too rigid to rotate the sigma bonds. You can't. So they have strain. So we're going to make a strained intermediate and then react it immediately. That's what's happening all day. And here we go. And we're starting off with halogenation of alkenes. And we got lots of questions and stuff here. Give a mechanism for each reaction below. I put an old reaction with our new reaction here. So the old reaction, and I'm looking for my pen. Uh-oh. This was not anticipated. I'm going to pause so I can get my pen. Pause share. Stop share. All right, we're continuing our activity now. Starboard right here. We're going to react HCl with a alkene. What is the first step in the mechanism? We can't see anything. We don't have anything. So you're looking at 6.1a hydrohalogenation in front of you right now. What is the first step in the mechanism? It will appear on the screen eventually, I promise. I'm using an arrow that starts at the pi bond and ends at the strong acids hydrogen. I know we can't see it yet, but it'll show up soon. And you made a carbocation. You remember that? You'll be copying this as soon as you can see it on the screen. You haven't missed very much, trust me. You make this carbocation major, and you don't need this one. I'm going to show it. But how do you know you don't need that second carbocation down here, the minor? Well, I know it's less stable, but in this particular exercise, it's not needed at all, is it? I don't have a product that results from it. I don't need to show it. So if this shows up on a test and you only have one product, you don't have to show me this minor cation. Okay? And what was the other product you made when reacted with when you reacted with HCl? Cl minus has lone pairs. We just need one of them. Makes a sigma bond. And I believe that takes you to the product. And there are, yeah. So we can't answer B yet because we have to do the mechanism for the other one. So I can do part D right now. Let's do D while we're here. Here's the answer to D. I would accept that as an answer for D. Delta plus on H due to lower, what's the magic word that goes in the blank? We have an activity right back there. Electronegativity. Wow. Good. D. So that makes sense. Why do electrons flow towards things with a positive charge? Because that's the only thing electrons are interested in. Okay. In the first step of 6.1D, right here, it looks the same, but you can't say it attacks that chlorine because it's positive, can you? Here's my answer for E. ClCl often has temporary dipole. And it looks like this. So talk to me in terms of what does this mean? Like, what happened to get to this position here? Clearly, the electrons in this bond are closer to one of the chlorines. Which one as drawn here, right or left? Electrons have a negative charge. If they are close to an atom, that atom starts feeling negative. So they are closer to this atom in this bond. So I will just show it. You know, here's the bond. There's the electrons. At this given instant, they're not halfway, are they? They're closer to the other one. And electrons are always doing that. In fact, that temporary dipole is the basis for the simplest intermolecular force called London dispersion forces. That's right. Well, the electrons are dispersing back and forth. So that creates temporary dipoles. Okay? So, yes, at any given instant, one of the chlorines might be positive, and then you attack it right there. You just pick one here. Okay? And that is not the end of this mechanism. I will write down the result of those two arrows. Please do not copy it. I will tell you when I want you to copy. These two arrows would give this result. You get a Cl here and a cation there. Why would you choose the cation there instead of, yeah, you're not copying this either. None of these are right. They're wrong. Wrong, don't copy. As opposed to, why is that first one a better choice than the second one? Tertiary carbocation has more of the big magic word that starts with H and ends with N. Hyperconjugation. So you didn't copy any of those down. I'm erasing the second one because it's even worse than the first unicorn. Okay, it's a unicorn. It's still a unicorn, but it's better than the other unicorn. Well, we're in fairyland now. I don't know why. There's something that chlorine has that hydrogen does not. In fact, if you want to be picky, it has 3 of them. And what are they? Lone pairs. So chlorine has 3 lone pairs. I just need 1. And during the first step, there's a 3rd arrow. You can't do this with hydrogen. Does hydrogen ever have a lone pair? Okay, I tricked you. Hydrogen in this course almost never has a lone pair. But there's this ion where hydrogen has a lone pair, and it's called hydride. And that's the only time you'll see hydrogen with a lone pair. Okay? We don't need that right now. But normally you do not put lone pairs on hydrogen. If it has a bond, don't put a lone pair on it. You're going to get OV -1. You never want that. So my question for you, the blue electrons that I just drew, are they going to come back to the tertiary carbon or to the secondary carbon? They're going to come back to the one that's spending more time with a plus charge, the one I drew. That's the better one, right? So show the arrow coming back, not in blue, in red, to the more substituted carbon. When I say that, we have this ring. Tertiary is more substituted than secondary or primary. I just haven't used that word substituted before. It just means has more carbons attached. So I'm going to use the word substituted a lot, and I don't want to have to explain it every time. So when I say substituted, it's basically the one with the higher degree sign, isn't it? That's all it means. More substituents, carbon groups, okay? So substitute. So we come back with the blue electrons, come back to the more substituted carbon, and we have a question. Oh, it's doing one thing. It got hit by a pair of electrons, and the result of that was to boot off the other Cl. And as that was happening, this carbon started feeling very positive. So before you even see a cation, this arrow happens. So yeah, you can think of it as the third arrow in a sequence, but they're happening so fast, you can't count them as like, oh, there's part one, part two, part three. They're too fast for you to see that. But it was a very good question. Her question was, you told us previously an atom can't do two different things. But in this case, the atom is accepting a pair of electrons that changes the nature of the atom. It's got too many bonds. Now it's got to kick off the other one, and it did that. But as that was happening, the carbon was developing a positive charge. So you never saw the carbocation. It's not seen in this mechanism. Trust me, they've looked for it. It's not there. So what you get is this. You get the Cl bonded simultaneously to both positions. And what shape is that? It's not very well drawn, but it is a triangle, isn't it? And if you do formal charges, you do realize chlorine started with 3 lone pairs. I'm putting them on temporarily. It now is down to 2. Why is it down to 2? Because you used one of the 3 lone pairs to make that bond in red. There's still 2 left. Now do a formal charge calculation. This chlorine owns 6 electrons. It owns 2, 4. Half of a bond is 1 more. Half of a bond is a 1 more again. That's 6. What charge does the chlorine have when it owns 6 electrons compared to on the periodic table where it owns 7? VII. Positive. It's called a chloronium. And because it's in a ring, it's called a cyclic chloronium. Okay? I went too far with that, didn't I? Yeah. Okay. Now, what I'm going to do is I'm going to show that, you made half of it like this. So you can copy it right now. Oh, we were copying already, Dr. Whitaker. So copy it now. And you get 50% that, and then don't copy this. Don't copy. You don't need it. It's extra. Wow. 50% this. You don't need 2 copies. I only have 1 product drawn, right? You don't need 2 copies. But anytime you do this, you're going to get a 50-50, right? You start with an alkene. What's the hybridization of the 2 carbons in an alkene? They're alkenes. They have a double bond. sp2. What's the name of that geometry? What's planar mean? Flat. So if you're a chlorine, Cl2, You can come in just as easily from the top. That'll give two wedges. Or from the bottom. That'll give two dashes. It is not possible for a chlorine to be bonded with a wedge to here and a dash the other direction. Think about it. It's a triangle. You can't have half of it above and half of it below. Okay? So those are your two triangles. You do not need the second one. Just keep in mind you form 50-50 every time. Okay? This is what you need. And what was the other product when you reacted with the Cl2? There's Cl number 1. What does Cl number 2 look like? Plus Cl minus. Try to change the color of my chlorine there. Okay. All right. So E. In the first step of 6.1d, it's not easy to see why Cl is attacked. And the answer is over here. It doesn't have a partial. How can this reaction work out? Well, it waits for it to have a temporary dipole for it to work, right? And then later, the chlorine is going to come in and attack one of these two carbons. It doesn't, this is just triangle, right? You said it's a triangle? It's got strain. It doesn't want to stay like this. The way to relieve the strain is to come in from the back side of the bond that I'm about to break. This bond is breaking and becoming a lone pair. Okay? Bond is breaking and becoming a lone pair. This is called backside attack. It's a new thing. Never seen it before. It's attacked by a nucleophile on the backside of what? Look at the product. What's that mean, backside? It means if I have an atom here bonded to another atom back here. I think that shows up on the screen. The backside of this bond is exactly here, 180 degrees away from the bond. What's 180 degrees from a dash? A wedge. Isn't the new bond to chlorine on a wedge? Now, the reason it had to come from the backside is these right here in this bond are electrons, right? Chloride is coming in with electrons. Do you think electrons want to come in from the front where there's already electrons? No, they're repelled by that. It wants to get as far away from those electrons as physically possible. So it comes in from the backside. As a result, one of the bonds ends up on a wedge. The old bond, which I didn't break this bond, did I? Look, it's there, it's still there. Stays the same. So why are they opposite sides? Because you did a backside attack. Anytime you have to explain why the geometry is anti, the reason is backside attack creates anti. Wow, that's not good. Creates anti-stereoselectivity. That's a big word. It's new. Although we did know the word stereochemistry from back in the day, last test, right? That's molecules that are similar, but they have different orientations of atoms, like R and S, right? And here, anti-stereoselectivity just means one is up and one is down. Now, we're going to see syn stereoselectivity Monday. Okay? So, where are we at? Have we answered all our questions? Why are there 3 arrows in the first? We didn't do that one, but only 2 arrows. Well, the main reason is Cl has a lone pair. Cl has lone pairs. which can make a bond. H does not. So there's your answer for 6 point. That's a part B. Okay. And which reaction is a lot faster based on your answer to B? Ladies and gentlemen, if you have two reactions, one creating octet violation, but here's a case where you have to have an octet violation. And another one where there's no octet violation. Every atom has full octet. That one fact is the answer. You're creating octet violations that's incredibly unstable. That's going to be incredibly slow. If you have another reaction that does not have an octet violation, your first instinct should be it's faster. And in this case, your instinct is good. Okay? There are other factors, but we're not going to explore those in this introductory organic chemistry class. Okay? So, I think we're doing okay. No OV. Good answer? That's a short answer that actually has everything I need. And then the first step is not easy. H and F. Why is H attack and not Cl? There was the answer right there with the charges. And I think we're done. Formal charge is okay. It has a full octet. You see it? It's got 2, 4, 6, 8 electrons around it, so that's great. Formal charge, not so great. But in terms of octet violation versus not, you can ignore formal charges. OVs are much more serious. And that's it for us on this one.